Okay, can anybody tell me, somebody tell me what's happening in week 1?
I think
Yeah, Rohan, go. Go on.
thank you. I think 2 commercials were, carried out, and there was almost $55,000 of sales that took place.
Okay, great, that's right. And Mr. Harima, can you tell me what happened in week 2?
Yes, in week 2 there were 5 commercials, and the sales was $57,000, I think.
Right, I guess so, yeah. Or no, I think it's
$5,700.
5,700, but
Oh, yeah,
whatever.
5,700. Yeah.
Right. We'll just say 57. Okay, good. So anyway, the point here is to ask or to think about or to wonder whether commercials affect sales. So this is okay. So how many columns are there here?
2 columns, 3.
3.
There are 3, but only 2 of them are really what we're talking about, or what we're thinking of as variables.
Yeah.
We only have 2 variables. What are they? Number of commercials and
And the
sales.
Sales.
Right. Okay. So we'd like to sort of analyze these in the same picture. We want to make a picture, i.e., we want to make some kind of analysis, and it's either going to be a graph or a table. In this case, it's going to be a graph. And so we're going to include both variables in this graph. And you'll see that it looks like this. Okay, so what do we see along the x-axis? We see the first variable, or one of the variables. It doesn't have to be the first one. But we see one of the variables, which is number of commercials. And what do we see in along the y-axis? The sales, the other variable. And forget about that line there for the moment. Just look at the dots. We have a bunch of dots. And what does each dot stand for in this graph?
The relationship between number of commercials and sales?
No. What is each dot? I mean, yeah, that's what all of the dots together show us that. But I mean, what does each dot individually stand for?
The amount of sales?
The difference.
Amount of commercial and the sale.
The position of where the number of commercials placed in a certain number, the certain sales.
Okay. Yeah, you're all right, but you're not saying what I want to hear.
The amount of money earned per commercial.
So, I'm pushing a certain things that I want you to learn in this course. And something that we talked a lot about maybe 2 weeks ago or 3 weeks ago, something like that. We talked a lot, maybe it was 4 weeks ago. So I want that. But what is it? How many dots are there here? How many dots are there?
10.
10.
Okay. So what does each dot stand for? Okay. What?
Each week.
Yeah, each dot is a week, right? Week 1, week 2, week 3, right? Does everyone understand?
Yeah.
See, if you look at a graph like this, it's really good. Anyway, before I say that, so remember, this is a set of data, right? We could think of this as a spreadsheet, right? And what do we call the columns of a spreadsheet? We call them variables, right? Does everyone know that, right? Well, okay, that's one thing. But what do we call the rows of a spreadsheet, or the rows of our data set? I made you do a lot of homework on this.
The observation?
Yeah, the observations or the elements, right? We used the word observation, element. I think we also used individual, right? Didn't we use all three of those words, right? Do you remember that?
Yes.
So what are the elements or observations in this data set?
Week.
The weeks,
Week.
right? Okay, that's the idea. So the elements are the weeks. What do we, what is each dot? Each dot is an element in the data set. Now, each element, each dot has an X coordinate and a Y coordinate, right? Everyone, of course, agrees with that, right? Each dot has an X coordinate and a Y coordinate, right?
Yes.
And those are the variable, I'm sorry, yeah. Those are the variables that we included in this data set. So the X and Y coordinates, in other words, the X-axis and Y-axis, are the variables that were included in this data set, right?
Yep.
So remember that we, let me draw this picture again, if I can. Let me go to here, remember that we, I think I drew something like this. So I said, well, maybe I didn't quite draw it like this, but this is called an element. And an element has many different attributes, right? Or an observation or an individual has many different attributes. So here, the elements are the weeks. So it's a week. And then the attributes are, there are many things about a week, even within a business setting, that we could measure. For example, we could measure the number of employees that week, number of employees. Or we could measure what else in a business? I don't know. We could measure the temperature, the average temperature in that week. I mean, nobody would really do that, but we could do that. We could do many things about a week, but in this study, we chose to look at the number of commercials. So that was one of these. So I'll just say that. That was like this one. And then this one is another attribute like here. Okay, but we could have used many, many different attributes. Or we could have chosen many, many different attributes. So what we're doing here is we're looking at the elements. I want to say it this way. We're looking at the elements, each element or each week. There are 10 of them. We're looking at the elements kind of through a framework or through a looking glass. And that is, we're looking at these weeks through the looking glass of number of commercials and sales. Does that make sense? But we could have looked at it through some other set of variables instead of these two, right? Does that sound too strange? Okay, so anyway, all right. So that's what we have here. And this is called a scatter diagram. So when you have something like this and you have a bunch of dots, that's called a scatter diagram. Okay, does everyone understand this? Now, once we have the scatter diagram, suppose we had this and this and this and this and this and this and this, then we might try to find what we call a relationship between the two variables, between X and Y. So in this one, we might say that the relationship looks like something like this. Well, that didn't work. Anyway, you know what I mean? No, maybe not. Let's try it again. Try it again. We might say that it looks like this.
dan K4L4. K4 N.
Okay, does everyone get the idea? Okay, so we're talking about, we kind of can see a relationship between this data, or we can see a relationship between these two variables, between these two variables, or between these two variables. Okay, and the types of relationships that we talk about are this type, and this type. Okay, so this type we say there's a positive relation. This type we say there's a negative relation. And by positive and negative relation, we mean that when if you go to the right, in other words, as the x-axis increases, if the y-axis also increases, or the y-coordinates also increase, that's called a positive relation. And here, as the x-axis, as the x variable increases, the y variable tends to, or the y-coordinate tends to decrease. That's called a negative relation. And here, there's like no, maybe no relation. Okay, is this clear?
Yes.
Any questions about this? Okay. So anyway, once more, what are the dots in this table? I'm sorry, what are the dots in this graph?
Week.
Yeah, they're the weeks, or the elements of our data set, right? They're the elements of our data set. And then each element has many variables, and we're focusing on two of them. And the x-coordinate tells you the value of the first variable, and the y-coordinate tells you the value of the second variable. Okay, does everyone get that? Okay. Now, on the other hand, we can also do something for, not, those were numeric variables, but we can also do something for non-numeric variables. So, for example, here we have a table, and we have, it says quality rating and meal price for 300 Los Angeles restaurants. Okay, so what are the two variables here?
Quality rating and meal price.
Quality rating and meal price, right. And this is also, what are the, what are the elements in this table?
Restaurants.
Restaurants. So, and so what are the variables that we're measuring for restaurants here?
Quality rating and meal price.
Quality rating and meal price. And one of them is numeric, apparently, and the other is not numeric, it's categorical, apparently, right? Okay, so let's see what they're going to do with this. Anyway, what are the different possible quality ratings that you see here?
Good, very good, and excellent.
Good, very good, and excellent. Yeah, that seems to be about all of it. And those are called, sometimes they use the word this, sometimes they call that the levels of the variable, if it's a categorical variable. So we might say that the levels for quality rating are good, very good, and excellent. Those are the different possible levels, sometimes we say that. Or anyway, the different possible values. Okay, now what are they going to do with this? So first thing they did was they just focused on the quality rating variable. So just the first column here. And we said that there were only good, very good, and excellent. And we see the relative frequencies of those. So you know how to do that. We've done it before. We just count up how many good there are out of the total, how many very good there are out of the total, and how many excellent there are out of the total. And we can figure out the relative frequencies or the percent frequencies, right? Everyone knows that, right? Everybody is familiar with that, right?
Yep, yep.
Okay. Now, what they're going to do is they're not going to treat this meal price as a number, as a numeric variable. They're going to categorize it. So I'm sure that we've done that before. And so what they're going to do is they're going to make categories like 10 to 19, 20 to $29, 30 to $39, and 40 to $49. Okay, so like, right? We've done that before, so I'll just accept that. So we have now we can make a table. So to make a table, we need two categorical variables. That's why they didn't want to leave meal price as numeric, because you couldn't really make a table with that. So if you want to make a table, you want to have two categorical variables. Otherwise, well, okay, so I'll just leave it at that. So what does this 42 mean?
There were 42 good quality ratings in a meal price between $10 and $19.
There were 42 what?
42 quality rating that was good.
Okay, you cheated. You didn't say it the way I wanted, but you said it correctly anyway. I wanted you to say something a little different. What did I want him to say? What does the 42 stand for?
Restaurants.
Yeah, there were 42 restaurants, right? 42 elements, right? So I hope that you begin to think of it this way. It works. It's more, if you think of it this way, the analysis that you works a little bit better. Anyway, there were 40. Okay, what does this stand for? Somebody else?
Six very good restaurants between $40 and $49.
Okay, good. So there were 6 restaurants that had a quality rating of very good, and the meal price was between $40 and $49. Right. Okay. And somebody else, what does this stand for?
6 elements.
Yeah, what does that one stand for? You could also say elements. That's right. Okay, what is the last one? The last circle stand for?
The last circle shows that there's no good quality rating element that is between $40 to $49 in meal price.
Right. Right. Okay, so we might, before we were looking at this, and we had some data like this. And we said, is there a positive relationship? Is there a negative relationship? Is there some sort of relationship between these variables, right? Right, that's what we did just a minute ago, right? Right, everyone remembers that, right?
Yeah.
Yes.
And we said, yeah, there's a relationship. We would say it's a positive relationship, right? Something like that, right? So it's a positive relationship, right? So, we're often in all kinds of studies, whether it's science or business or anything, actually, any place where we're kind of thinking, we're often trying to make relationships between things, or find relationships between things. If you maybe when you're going to get a meal in the cafeteria at school, you might say, you might decide, should I pay at this counter or this counter or this counter? You're sort of looking for a relationship, like, which one is going to give me the shortest waiting time or something like that. Anyway, in many, many situations, we are looking for relationships, and in science and business and and in analysis, we're often looking for relationships between variables. But the variables here are numeric, but here they're not numeric, right? These are categorical. Right? But still, that doesn't mean that we're not going to be looking for a relationship between these variables. So what, if you were thinking in that way, what would you be thinking about in this particular table 210? What would you be looking for example? What would you be looking for? So I still want to do the same thing. I want to know like I can tell you that if you do a master's thesis at APU or you do an undergraduate thesis at APU, you might be, the focus of your whole thesis might be to show whether there's a relationship between two things. That would be like a whole thesis. Okay, so we're often interested in that. Now, how about here? If you apply that approach to this table, what are we thinking about?
Professor, I think that one relationship we might be looking at is price related to quality.
Yeah,
of service.
Right, right. Isn't that that's a very natural thing to think about, right? Does the price have some kind of bearing on the quality rating, right? That's an interesting question. So how would you know that? By looking at this data. Let me go back here and get rid of this. And this. So how would you know that by looking at this data?
Yeah, Professor.
Yes.
What I'll do using that data is I'll create a scatter graph.
No. I don't want to use a scatter graph because I don't want to use a scatter graph when we have non-numeric data. So let's not do that. I'll try and explain why we wouldn't want to do that, but let's not do that for now. So give me another approach.
All right, so if we were to use this cross tabulation of quality rating and meal price, I would assume that we would be looking at the highest number in the column for total. So as we can see, the highest number is 150 elements, and we can see that the quality rating for that is very good, and we can see the price for that is also the highest. So from this, we can deduce that the relationship between quality rating and meal price is we gotta find this sort of sweet spot, and that sweet spot, based on what this cross tabulation is telling us, is that the sweet spot is very good in quality rating and more reasonable in the price, between $20 and $29. So that if we're looking at the highest elements to determine the relationship.
That's interesting. That's a very interesting approach. So he said, let's focus on the highest number, which means in this case, the highest number of restaurants, right? Because the numbers stand for the restaurants. So he said, let's focus on the highest number. And he said he noticed that the highest number was, the quality rating for that highest number was very good. And meal price was between $20 and $29. Okay. So that would, I don't know, how would we use something like that? I guess that might tell you that, I don't know how a business would use that, but they might use it somehow.
If I may, I could propose one reason of how a business may use that.
Okay, please do.
So different businesses have different brand images, right? If we were to take that into the context of, let's say, the restaurant industry, for example. Different restaurants have different brand images. Some restaurants might have a brand image of cheap and affordable food. Some restaurants might have the image of a higher quality but higher priced food. So this is relevant to us because this restaurant in particular could be more of a middle ground where you have decent prices like $20 to $29, and for not average quality but not exactly the pinnacle either. So it coincides with our brand image very well, and our customers, it coincides with the customer's expectations from our brand. So that's why this information can be very valuable in a business application.
Okay, yeah, I think that would be very useful to maybe an investor or maybe somebody who was thinking about starting their own restaurant. Okay, now let's go back to this. So I circled this. So again, what does that mean? It means there were no restaurants that were very expensive and had a kind of a low quality rating, or they were only marked as good, not as excellent. Okay, so let's keep going. Let's see what they say here. Okay, let's start out here. Well, one thing we could do in this is we could figure out what percentage of the restaurants, well, we already did that, sorry. Okay, let's not do that. Let's read what they say here. Of the restaurants with the lowest quality rating, good, we see that the greatest percentages are for less expensive restaurants. So let's look at that. For restaurants with the lowest quality rating, most of them are what? Are cheap.
Very
right?
good or excellent. Oh, never mind.
For this row, for the row of good rating, most of the restaurants are what?
Cheap.
Cheap.
Are cheap, right? Now for excellent, it's the opposite sort of, right? For excellent, most of the restaurants are expensive. And in the middle, it's sort of in the middle, right? Very good is sort of average priced, sort of. So we can see that as we increase the quality, the price does tend to increase, right? And vice versa. As the price tends to increase, the quality also tends to increase. Now, it's not a perfect correlation or relationship here, but it does seem to be true. Okay, so we can talk about that kind of relationship in this data by making this is called a bivariate table or a bivariate analysis. So why do we use this word? So let me just show you. So why do we use that word?
There are two types of variable.
Yeah, there are two variables, right? What does variate mean? Or what is it referring to here? Variate means variables, and bi means?
Two.
Two.
So it's called bivariate. So this is called a bivariate table, or we're doing bivariate analysis. This is also bivariate analysis because we have two variables. These happen to be numeric and these happen to be categorical, but we still have two, so we can still call them bivariate. Okay? Okay, let's go on. I'm not going to cover this thing called Simpson's paradox, but you can look it up. If I were you, if you're going to look it up, they mentioned Simpson's paradox here, or in our text, I believe, in terms of categorical variables. But I think it's actually a lot easier to understand if you look at it, if you look it up in terms of numeric variables. So they explain it with an example of categorical variables, but I think Simpson's paradox is much easier to understand if you look at it in the case of numeric variables. But anyway, they don't do it that way here. But if you want to look it up, I would do it that way. Okay, so we did this, we did that. All right, now let's talk about how to deal with bivariate data in Excel. So using Excel for tabular and graphical presentations. Okay, so let's see, are we going to do this? Well, this is, how many variables are we dealing with here?
Two.
5.
5.
Oh.
Wait, what?
You already made these graphs, so you should be familiar with this. How many variables are we dealing with?
Isn't two?
Two.
Two.
Two. What are they? What two? I don't see two, but if you tell me, what are the two?
Here's one.
There's only one, and it's frequency.
No.
It's soft drink.
No, not only one in its frequency. So we have this, right? We have soft drink. And what are the values that soft drink can be? Coke Classic, Diet Coke, Dr. Pepper, Pepsi, Sprite. Okay, so that's the variable, soft drink. What kind of variable is it? Is it numeric or is it categorical?
Categorical.
Categorical. So we're dealing with one variable. It is, in this case, soft drink. It's categorical. And then all we do is we have the frequency here for the count. So apparently there were like almost 20 cases of Coke Classic and maybe 8 cases of Diet Coke and so on, right? So this would be like whatever this is, 18. Oh, there it is, 19. Here it is, 19, and then 8, and so on. But there's only one variable here. In this, okay, actually, here's the original data. So this is the brand purchased, okay? And there was first brand was Coke Classic, the second one was Diet Coke, and so on. And from this list here, they made this table, right? And then from that table, they made this picture. Okay, so that is one variable. Okay, let's take a look at, that's sort of the same thing. Okay, we looked at this data before. And this variable is called what?
Q to the right.
This variable is called audit times.
Data.
Okay, that variable is called audit times. And here's the data here. And they made this table out of it. So they converted, this is numeric, right? This is numeric. But what did they do here?
They like categorize it.
What?
They categorize it, like the numeric data.
Yeah, they made it into categorical data, right?
Yeah.
And I think I used the word at some point called binning. Binning it. We bin it. We put it into bins. You know, bins are like bottles. So we put it into bins. So like this one, 12, maybe that goes to the first bin, and then so on and so on. Okay, so we did that before. Okay, now, how many variables are there here?
2.
2.
2, right. And they are the number of commercials and the sales volume. Okay. And here, this is called a scatter diagram because both of the variables are numeric. Okay, and we saw that already. And what else? So pivot table, I'm not going to do it right now. Maybe we'll come back and do it. Okay? All right, so that is the end of chapter 2. Any questions about this?
I just have one question relating to relationship and correlation. So what's the difference between relationship and correlation, or is correlation simply one type of relationship?
So that's a great question. Let's see. So so let's just talk about what we mean by this word, relationship. Okay. So basically, what I mean by relationship between X and Y. So what do we mean by that? So basically, what we mean is something like this. Okay. So the idea is, by relationship means if you know the value of one of the variables, here's X and here's Y, the two variables. So if you know, for example, that X is quite low, or anyway, you know the value of X, does that assist you in knowing the value of Y? Okay, so we can think about this diagram compared to, or this data compared to, let's say this one. Okay, let's try this one. It looks like this. So something like that. Okay, so here, if I know, say X is down here, or X, I know the value of X, like for example, if X is low, does that assist me in knowing what the value of Y is as compared to here? So what about in this picture, in the blue picture? If I know that X is low, what can I say about Y, if anything?
I guess you can say if X is low, you can see where Y starts off when X is low. So does Y start off from the very bottom of the graph? Does it already start high in the graph?
Yeah. So what I mean by that question is, if I know that X is low, then I have a pretty good idea that Y is going to be between here and here. In other words, y is fairly low also, right? Whereas if I know that x is high, maybe up here, then I know that y is also going to be high, right? So maybe sort of about here, right? So if I know that x is low, then I know that y is going to be a sort of low also. Okay, so for this data, I would say x and y are related. Because if I know x, I have some idea of what y is. I have some information about the value of y. So that's what I mean by related. As compared to this data here, if I know x is low, y could be here, could be here, could be here, could be here, could be here. Right? It could be anywhere. Does everyone understand that? And if x is high, y could also be basically anywhere. So knowing the value of x doesn't help me at all in terms of knowing what y is. Does everyone understand that? Hello?
Yeah, that makes it a lot clearer.
Okay, so I hope that everybody's paying attention. So anyway, so that's what I mean by relationship between x and y. So if x is, so in the blue one, if x is low, I have some idea that y is also going to be low. Now it doesn't have to be that picture. It could also be this picture. Let me go back to blue, or let me go back to another color. Try. Okay, let's try yellow, even though you probably can't see yellow. Let's do yellow. Okay, you can't see that. So I'll use a different color. Let's say that. So how about this?
Yeah, on the
It is same as the blue.
What?
It is the same as the blue, but
Right, it's the same as the blue. So if x is low, I can make some kind of prediction about y. In this case, I'll say y is high. If x is high, I can also make some kind of prediction about y. In this case, we'd say y is low. So there's a relationship in this picture as well between x and y, right? Everyone agree with that?
Yes.
Okay, one more. Let's do one more. Let's do one more. Let's say, okay, I'll use red. Let's say that we have one more. Let's do this one. Okay, so now for the red graph, we can also ask the same question. Is there a relationship between x and y? Now, in the previous examples, two of them we said there was a relationship, and one of them we said there wasn't. So the one that didn't have a relationship was the green one, but the other two we said there were relationships, because if we knew about the value of x, we could make a reasonable prediction about the value of y. That's what we mean by a relationship. But I didn't, so, but these, we would say there's a linear relationship. So you can see why we'd call it linear, because basically it seems to fit a line, right? Something like that, right? Now clearly, this doesn't fit a line very well. I mean, I could draw a line there, but I don't really want to do that. I could, but it's not really a good picture if I do that. But the question isn't whether there's a linear relationship. That's not what I'm asking for the red one. I'm just asking, is there a relationship? That means if you know something about X, can you make a prediction about Y? So what's the answer to that?
Yes, there's a relationship.
Yeah. So if I know that X is down here, yeah, I'm kind of confident that Y is going to be between here and here, maybe. And if I know X is up here, call it in the middle, then I'm kind of confident that Y is going to be between here and here, for example, or whatever that is. And then if I know X is up here, for example, I'm also confident that Y is going to be, somewhere. I can make some kind of good prediction about Y. Okay, does everyone understand? So it doesn't have to be a linear relationship to say there's a relationship. It just means there's a relationship. There's some relationship between the two variables. Whereas, like we said in this one, there's no relationship, right? If I know about X, it doesn't help me at all in knowing about Y. Okay, does everyone get that?
Professor,
Yes.
couldn't the red one be like a polynomial?
Yeah. The red one would be like maybe it would fit a polynomial or something else. Yeah, in this case, it definitely looks like a polynomial. Yeah, but that would be the second step, is to say, well, what is the relationship? What kind of relationship? And that would be like, is it a linear relationship, like this one or this one, or is it a not what we call nonlinear, or like a polynomial relationship? Or I might have had a different graph. Maybe I might have had this one. So I might have had this picture. Maybe it looks like this. Okay, so that would be something else, right? That wouldn't be a parabola. It wouldn't be a quadratic relationship, but still there's a relationship, right? If you know X, you know something about Y, right? That's what we mean by relationship. Now, the only picture I've drawn so far where there's no relationship is the green one, right? Because there, knowing what X is doesn't give me any clue about what Y is. Okay, that's the idea of relationship. Now, somebody used the word correlation. How do I spell correlation?
C-O-R-R-E, L-A-T-I-O-N.
Okay, so there's only an L. Okay, good.
Thank you, Yohei, for the spelling.
Okay, there's only one L. Okay, so that word
My bad.
definitely has to do with the concept of relation. And so we can talk about, we may as well mention that now. So let's say, briefly, let's just give a brief explanation of correlation. So here's one graph, one data, and here's another. Choose a different color. Okay, and let's say we're going to use blue dots. Okay, so here, we have one set of data, and here we have another set. Okay, everyone see the difference? So if I know, so are there relationships between this one and here, X and Y? Is there a relationship between that X and Y?
Yes, Professor.
Yes.
Yes.
And how about this? And how about this X and Y? Is there a relationship between this X and Y?
Yes.
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 So we both have relationships, but now we want to talk about, remember, what did we mean by relationship? We said how, if we know that X is somewhere, how much of a good prediction can we make about Y, right? That's what we said. So how good a prediction can we make about Y? So if I know that X is here, let's call it X low, then I'm going to say Y is between here and here, right? Does everyone agree with that?
Yep.
On the other hand, suppose I go to the other picture, which was here. If I know that X is low here, now the range of Y is going to be much narrower, right? It's going to be like here to here, or something like that, right? Right? Does everyone understand?
Yes.
Yep.
Okay, so I'm going to say that when I make a prediction here, I'm going to be much more confident about my prediction. More confident than here, not so confident. Okay, does everyone understand what I'm saying? So here, if I make a prediction, I'm gonna say it's between here and here. So, but actually, if you fit a line to this, let me do that too. Let me fit a line. Let me draw a line in there. So here, let me draw a line here. There's that line. And let me draw another line, a line here also. Now the line is what we use to make the prediction. That's the purpose of the line. Okay, so if X is here, then my prediction for Y is going to be here. Everyone understand that?
Yes.
And here, if X is low, then my prediction for Y is going to be there, right? Sorry about that. You know what I'm trying to draw, right? So everyone agree with that?
Yep.
But so I'm going to predict here, and I'm going to predict here, right? Everyone agree? Everyone agree with that?
Yes.
Yeah.
But which prediction am I going to be more confident about? The top graph or the bottom graph?
The bottom.
Bottom, right? Because why? The range is much narrower for the bottom one than it is for the top one. So I'm going to be much more confident in the prediction in the bottom one than in the top one. Okay? And the correlation is some way to measure how. So basically, what am I saying? I'm saying that here, the dots are kind of far away from this green line, right? As compared to this one. So in the top picture, the dots are sort of far away from the green line, whereas in the bottom picture, the dots are very close to the green line. So I'm more confident when I make a prediction for the bottom picture than for the top picture. And the correlation or the correlation coefficient is going to tell me that. So the correlation coefficient for this is going to be about 0.95, and the correlation coefficient for this is going to be about maybe 0.75 or 0.8. Okay, so 0.75 and 0.95. So the correlation coefficient, we will discuss it more clearly later, but it tells you how close the data fits a line, how close the data fits a line. And this data on the bottom fits, and I'm sorry, the correlation coefficient is always between 0 and 1. Sorry, wrong. The correlation coefficient is always between -1 and 1. So we usually use the symbol R for the correlation coefficient. So it's always between -1 and 1. So here it's 0.95. That's almost 1. So that's almost perfect. So a correlation coefficient of 1 would mean everything falls exactly on a line. So it's pretty close here, but here it's not as close. Okay, is this clear?
Yep.
But going back to this picture, this data is pretty strongly related. This red data is pretty strongly related. Wouldn't you agree? There's a pretty good relationship, pretty strong relationship between X and Y. Wouldn't you agree?
Yeah.
Yeah.
In other words, if you know X, you can make a pretty good prediction about Y. But if you check the correlation coefficient of this data, it's not going to be very good. Like the correlation coefficient might be, I'm just guessing, but it might be like R equals 0.55 or something like that. I'm just making it up. I don't really know what it is. Okay, so it's not going to be very good, or maybe it's even lower than that. Because the correlation coefficient measures how well the data fits a straight line. And this data doesn't fit a straight line very well. Okay, so you have to be careful about that. When you say data is not correlated, this data is not very doesn't have a good when people use correlation, they mean linear correlation. So if you say this data is not correlated, you know, somebody else might misunderstand that and think that it's not related or there's no relationship, but that's definitely not true. There's a strong relationship between X and Y, but it doesn't have a high correlation coefficient because it's not linearly related. So you have to be very careful about that. It's kind of a bad choice of words in the statistical language, because people, you know, when you think of the word correlation, you mean, you know, if you say it's got very low correlation, you immediately think, oh, it's not related. But that's definitely not true. Okay, so that's a bad decision that scientists made to use that word, correlation.
Professor Cluster?
Yes.
Yes, I just want to reconfirm then in layman's term, okay? So correlation is how two or more variables, basically how variables are related to each other, while correlation coefficient measures how well a graph fits in a straight line. Is that correct?
I don't think so. Well,
okay,
in layman's terms, maybe in layman's terms, that may be the way it's used, but that would be sloppy. Okay, so yeah, if you want to say, you know, people who use the language incorrectly, in other words, laymen, they might be using it that way. So yeah, maybe, but it's.
I understand. Please clarify then.
Well, no, you said it yourself already. So correlation should mean correlation coefficient, or should mean linear correlation. But like you said, laymen don't always use it that way. But you should be aware of the fact that there could be misunderstanding or misinformation because of that. Okay?
All right.
Okay. Okay. So, all right. So we talked about, so what did we talk about today? We talked about bivariate. Remember this? Bivariate data. So what does bivariate data mean? Where's that word?
Data with two variables.
Yeah, I thought I wrote it down somewhere, but I don't see it here. But it means two variables, right? Oh, here. Maybe I wrote it here. No. Anyway, What does bivariate mean? It means we're dealing with two variables. So we talked about bivariate data today, and we talked about if the data is numeric, then we can do a scatter plot. And if it's not numeric, then we do a table, or what's called cross tabs or cross tabulation. Okay? And then we're often looking for relationships between the two variables. When we're talking about bivariate, we have two variables. We're often looking for relationships between the two variables, and we can look at it in a table. It's not quite as easy to see in a table, or we can look at it when we're dealing with numeric data. These pictures are all numeric, right? These pictures were all numeric. There are no tables here. We're talking about numeric data here. Correlation coefficient is for numeric data. Okay? So anyway, these are all numeric examples, not tables, not categorical data. And we talked about what we mean by correlation, or sorry, what we mean by relation. And then we also talked about what we mean by correlation. Oh, that's interesting. I never thought of that. Okay, you see what I'm talking about? See what I'm talking about?
Yep.
What? The word correlation has the word relation in it. Right?
Yeah.
Okay. And it means like co-relation or, but anyway, okay. Okay. Any questions so far? All right, let's move on. Let me just reset up my desk here. So I'll just stop the video for a minute. And I'll just reset up my desk here. And we're going to move on to chapter 3. Sorry about that. Okay, so let's go to chapter 3. And, okay, let me just go to chapter 3. Okay, let me go to, okay, I want to go to here. And okay, let's go to chapter 3, and we'll resume the previous style, which is we'll have a short lecture and then questions. So the first one is simple. Oh, we did that, summation. We did summation already. Okay, so let's go to here. And I will share my screen with you. Okay, can everyone see my screen?
Yes, Professor.
Yes.
Yeah.
Okay, so let's take a look at this.
Okay.
And let me just do one more thing here. Okay, let's watch this. Okay, so now we know what this means. And if we have, so actually let's try this one. Xi, I equals 1 to 4, let's say. Okay, so again, it's the same thing. So what do? We do x1, I'm sorry, we put in I equals 1 here for I, so we get x1. Then we put in I equals 2 here, so we get x2. Then we put in I equals 3, then we get x3. And then we put in I equals 4, we get x4. And then, because it's sigma, we put in plus. So that is what this means. So this means that, right? Now, let's go back to what we said was the mean. So if we have these numbers 2, 4, and 10, and we want to know what's the mean of these three numbers, we take 2 plus 4 plus 10, and then we divide by 3. And we said in general, if you have x1, x2, up to xn, then you want the mean of them. You're going to do x1 plus all the way up to xn and divide by n. Whoops, sorry about that. I don't know why it does that. I mean, anyway. So anyway, you saw that, right? Let me write it again. x1 plus xn over n. Okay, but now we can say, oh, I know how to write the top part. I can write the top part as sigma, we just did it. Well, we only did it for 4, but sigma xi, I equals 1 to n. That will give me the top. That will give me this part here. So, look at that. Then if I want to divide by n, I just divide by n. And that is x bar. Okay, so we now have a sort of another way to write x bar. Besides writing it like this, we can write it like this. Okay, so let me write it again. X bar equals sigma xi, I equals 1 to n over n. And that's for something like we said before, x1 up to xn, a sequence like that of numbers. Okay, so now we have an expression for x bar here. Now, going back to here, you probably know that you can just, to calculate this, you can either type in or you can just point and click. If you want to point and click, you use up here and you use this one, the mean or the average. And it guesses that you mean from C3, from here to C8. So, and that is what I wanted. So I can just hit enter, hopefully, and it will give me the average. So, by the way, the answer was 8.5 for that original question. Now, if you don't want to use the point and click method, you could just type equals, and then you have to type out the word average. And then you can do that, and you could type in the cell range, or you can click inside there and then drag through, either way. Okay, and you get that. Okay, so anyway, that's how we can do that in Excel. Okay, now let's go back to our text in the next video. Okay, so now we're back at the book. We're talking about the mean. We already explained it, but perhaps the most important measure. Okay, let's read what I wrote up here at the top. In the video for the mean, sometimes we use x bar and sometimes we use mu. And you will see that sometimes the denominator is n and sometimes it's n minus 1. If we are inferring or guessing about a population mean from a sample, then we use n-1. Otherwise, we use n. So let's see. I don't know if that will become clear or not. Let's see what happens here. Measure of location is the mean, or the average value for a variable. The mean provides a measure of the center, or they call it the central location. But the center for the data, right? The mean tells you kind of the center. Okay. If the data actually, I'm going to skip this. I think for a sample. Now we've talked about the difference between a sample and a population. I hope. I think we have. The mean is denoted by x bar. If the data are for a population, the mean is denoted by the Greek letter mu. Now I'm going to pause here because I'm not sure if we talked about the sample and the population. So I'm going to just pause here. Did we talk about sample and population yet?
Well, we didn't, but I guess there was a bit relating to sample and population in Han Academy. Yeah, there was.
Yeah, it was covered there, but we haven't actually spoken about it at length in class.
Yeah,
Yeah, in
at least
class.
from my
we
notes.
haven't talked about it, sir.
Okay, thank you all. Okay, let me just go through this. So hopefully it won't take too long. So let me just at least remind you or introduce you to this concept. So in statistics, sometimes we have a big population. Suppose we're talking about all the students at our university. But suppose I want to know the average height of all the students. Now let's say we have a total of 6,000 students. So we could actually go out and measure all 6,000 people and find their heights. We could denote it by x1, first student x2, x3. The first height is x1, the second height is x2, the third height is x3. We go all the way out to x6000. We could do that. And then we just do what we already discussed. We do sigma I equals 1 to 6,000 and divide by 6,000, right? So we could do that and we would get the average. But oftentimes we don't want to do so much work. And if the population wasn't 6,000 but 6 million, suppose we were talking about a whole lot of people, we wouldn't want to do that. So we can denote the whole population here. Maybe this is all the students, and we'll call that the population. And it has x1, it has x2, x3, it has x700, it has x5761, and so on. It has all the people in there. But we don't want, suppose, to do all the work of measuring everybody's height and recording all of that. So we can typically, we will take a sample from the population. So we'll only take maybe 50 people or 60 people or 20 people or 100 people. But anyway, not the whole population. So we could just, I'll draw it like this. I'll say we'll take a sample. So we'll take a sample. So we'll call this the sample. So the population, let's say, we use the capital N to denote the size of the population. And let's say the sample, we use a small n for that, is 100. Okay, so suppose we have the sample of 100. Now it's easier to calculate, to measure all 100 people's heights instead of 6,000 people's heights. So anyway, we have x1 here, and we have maybe x20 in there, and x5230. But whatever, we only have 100 of them. That's a sample from here. So we have 100 elements in here, which are drawn from the full population. And then we can, what are we trying to do? We still want to know what's the mean for this whole population, but we're only going to calculate the mean for this. Now, obviously, the mean of this doesn't have to equal the mean of this. But anyway, we're going to calculate the mean of this. Now, I'm going to use this, it's not really right. I'm going to say it's x1 plus x2. I'm assuming like we got the first 100 people, which is, we don't want to do that. But anyway, I'm just going to say this means the 100 people. So here I didn't really take a random sample, or I meant it that I was taking a random sample, but I use this notation of x1, x2, x3. So you might just think I got the first 100 people, and that is not really random. But anyway, I was just using the notation in that way. So anyway, we're just taking 100 people, and then we're going to divide. And we're going to take 100. How do I erase? So we're going to take the 100 people and calculate their mean, and we're going to call that x bar, like we said. But for this, we're not going to use x bar. For the mean of the whole population, we use a different symbol. We use this symbol mu, which is, I think it's a Greek M. Mu, M-Y-U. Anyway, whatever it is, we're using that. So this is what we're trying to know, but we aren't going to actually calculate this. We're only going to calculate this. We're going to call that an estimate of mu. So x bar is called an estimate of mu. It's not, obviously it's not going to be equal to mu. It's unlikely that it's going to be equal to mu. It only estimates mu. And if we took, anyway, if we took a different sample, we would get a different x bar. That would still be another estimate of mu, but you know, obviously they're not necessarily going to be the same, and they're not necessarily going to be the exact value of mu. When we're doing things from the sample, like here, we're calculating the mean of this, we don't use a Greek letter. We use a non-Greek letter like that. But when we're talking about things in the population, we use a Greek letter, and so we use mu. We're going to call that an estimate of mu. So x bar is called an estimate of mu. It's not, obviously it's not going to be equal to mu. It's unlikely that it's going to be equal to mu. It only letter, we use a non-Greek letter like that. But when we're talking about things in the population, we use a Greek letter, and so we use mu. And we also use a different word. When we're talking about something from the population, I just said we use Greek. So for example, in this case, for the mean, we use mu, and we call it a parameter. So Greek letters are for parameters. When we're taking something from the population, I'm sorry, from the sample, when we're doing some calculation based on data in the sample, we don't use Greek. I guess we call them Roman letters. We use Roman letters like x bar. Well, x bar is not Roman, but x bar, and we don't call them parameters, so it's kind of a strange word. You'll think statistic, I think it's a strange word, but we call it a statistic. Okay, not a parameter. So a statistic is something from the from the sample, and a parameter is something from the population. So let's say that again. A statistic is something calculated from elements of the samples. A parameter is something calculated from the population. So, or from the whole population, I guess I should say. And for parameters, we use Greek letters like mu. And for statistics, we use non-Greek letters or Roman letters. Now, what does this mean? Why do we use that word statistic? So you might hear the new economic statistics came out for this month for the economy. So what does that mean? That means to me that the new economic numbers for the economy came out today. The new statistics for the economy came out today. That means what? If they're using the word correctly, or at least in the statistical sense, it means that the new numbers that we got, like for GDP or whatever, unemployment, if they're saying those are statistics, and if they're using that word in the statistical sense, then it means that these that came out are only from a sample. So we don't really know the true unemployment number. We only did a kind of an estimate of the economy by taking some sample from the economy and finding out what was the unemployment there. So they don't ask every single company. They only ask a sample of all the companies. And so we call that a statistic. So when they say the new statistics for the economy came out this week, I think that's what they're saying. That the implication is that it came from the as a sample of the entire economy. If I guess you'll never hear it, but they say the new parameters for the economy came out this week, and unemployment parameter is 2% or something like that. No, you don't hear that. They never say that. And I think that we can assume that when they use the word statistic, they are using it correctly in the statistics sense, and that is that this means that it comes from a sample of the whole economy, not the actual population. Okay, this was a little bit of a long video. Okay, so the point is that what do we call things that come from the population?
Sample.
Yeah.
Okay, sample. Samples come from the population, but when we calculate some characteristic of the population like mu, what do we call it?
Parameter.
Parameter. When we calculate something from the sample, what do we call that?
Statistic.
Statistic, right? So statistic comes from the sample, parameter comes from the population. And in terms of the letters that we use, for a sample, we use Roman letters, so we use X bar here. And for the population, we use Greek letters. So Greek, parameter, population, Roman letter, statistic, sample, okay? But we have reviewed or covered this concept of population versus sample. And we also have said that we're going to use Greek symbols for population and non-Greek for samples. And we're going to call things from the population parameters, and we're going to call things from the sample statistics. And we also said, except for one thing, and that I don't know why, but I mean, there's no good reason why, but we don't use anything Greek for this. We use capital N. I don't think that's a Greek letter. I don't think it's a Greek N or anything like that. So this is one exception. We use a Roman letter even for this population. Okay, but otherwise we follow these conventions. Okay, it looks like we don't even have time for one question. So that's too bad, but we'll do it next time. So next time we'll continue with chapter 3. And as I said, you have a lot of homework this week, but you won't have anything in Khan Academy this week. So you can get to work on the homework though. Okay, any questions?
Do we have any
Attendance.
response code?
Do we have any what?
Response code. The code for respawn.
Yes, we have. I will share now.
Ah, I'm sorry. Right. Thank you.
Hello?
Yeah, go ahead.
Okay, I will share now.
Any other questions? Okay, thank you for coming. See you next week, and get to work on the WebAssign homework. Okay, that's all.
Sir?
Yeah.
Will there be any changes on the due dates on WebAssign, or should we do as it is?